Good morning, everyone, and again, thanks for attending. And as Dean said, my name is Eric Weber. I'm an applications engineer here at Linux, and today I'm going to give you an overview of some of the additional capabilities SOLIDWORKS Simulation Premium offers that go beyond those included in SOLIDWORKS Simulation Professional. So today I'm going to be using this PowerPoint presentation that will give us a general overview of the capabilities. It does a nice job of kind of bringing everything all together, as well as jumping over into SOLIDWORKS and actually showing you some examples. So as most of you already know, SOLIDWORKS Simulation and Simulation Professional cover many different types of studies. With simulation, we have two different, we have three levels. The first being just SOLIDWORKS Simulation, then we have SOLIDWORKS Simulation Professional, and then Simulation Premium. So with simulation, we can do linear statics and basic motion studies, and then Simulation Professional gives us additional study types for more complex analysis, and that was the topic of our last webinar in this series. So if I click into our Simulation Premium, this gives us the general overview of all of the different modules that SOLIDWORKS in the SOLIDWORKS Simulation Suite. So the first suite, kind of over here in light blue, are linear static analysis for parts and assemblies, as well as basic motion analysis. So last time we talked a lot about SOLIDWORKS Simulation Professional, which gives us these 10 additional capabilities, these 10 major additional capabilities. The first being 2D simplification, and submodeling are a couple of tools some additional tools that you get with Simulation Professional, and then some additional study types that we're able to run with Simulation Professional are going to be frequency, buckling, fatigue analysis, pressure vessel analysis, drop test, and then a thermal study, which is actually kind of a whole different type of study, because we're doing thermal studies looking for temperatures rather than structural studies. But then also we get the capability to do optimization for automatically optimizing your designs, as well as over in the motion solver, event-based motion, which allows us to do some more complex motion studies based on sensors and timing. So the topic of this webinar is going to focus on SOLIDWORKS Simulation Premium, which is over here on the right side. Now you'll notice on this slide there are a light gray rectangle and a dark gray rectangle. So these represent everything that's included with these different packages. So at the Simulation Professional level, you not only get these additional capabilities, but you also get linear static analysis. And the same goes for Simulation Premium. If you purchase Simulation Premium, not only do you get the premium modules that I will talk about, but you get everything else below it in the Simulation Professional and in the simulation package on the right side. So with that said, I think I'll start to kind of get into more details on some of these Simulation Premium modules. So the first thing I want to talk about is linear dynamic analysis. So a lot of you are probably familiar with linear static analysis, and some of the assumptions we are making in that is, our models are fixed in space. They're statically fixed, in all three directions, and also our loads are static, meaning that they're slowly applied and kind of held on. So these are good for loading cases where a frame is a good example, where we have some weight applied to this frame, and it's just kind of sitting there. Whereas with dynamic analysis, now our loads can actually be input as a function of time. So we can have time varying loads that also give us time varying responses. So when I say response, I'm talking about things like displacements and deformation, as well as stresses, as a function of time. So diving a little deeper into linear dynamics, there's actually 4 different types of studies we can run with linear dynamics. The first is a time history or transient study. So this is This is basically entering in a load as a function of time and getting a response as a function of time. Very good for shock or very, high frequency or very quick events. So this allows us, again, to actually enter in a load case that changes over time, and then also allows us to look at the responses as a function of time, where we can actually control, do I want to see, do I want to see a stress plot or a displacement plot every, half second or whatever if we're running a study like that. So again, the first is the time history. The second type of analysis in linear dynamics is a harmonic analysis. So a harmonic analysis allows us to enter in a load case based on a frequency. So our load amplitudes can vary as a function of frequency. So these are typical harmonic studies are typically done, in areas where we have frequency-based input. So a good example would be rotating machinery like engines. If you've got machines in a warehouse or workshop, or if you've got, if you're mounting something near an engine on an automobile or something like that, where the amplitude of your events change as a function of frequency. So how fast the motor is rotating, for example. So not only can we enter the loads in as a function of frequency, but we can also get our responses as a function of frequency. So with this, we can actually see, okay, what frequency will give us the highest response. So, what RPM of our engine, or, what RPM of the motor running a assembly machine or something like that. So harmonic analysis, again, it allows us to look at load inputs as a function of frequency and responses as a function of frequency. Again, displacements and stresses as a function of frequency. Next is random vibration. So oftentimes it's hard to characterize an exact time history loading case, because you have all these small random events, and these random events happen over a long period of time. So random vibration allows us to capture very complex loading cases and also longer duration events. The transient study that I mentioned first is good for short duration events because we're solving a lot of equations, and depending on our time step, we could solve many different time steps within that. Now random vibration is more efficient at accomplishing that. So not only do we have a random load, but we can also capture this over a whole load case. A good example with random vibration is, for example, like a car driving over the highway. There's a lot of different events that can happen. You could hit a pothole, you could hit a small bump, you can be turning, you can be doing all sorts of things, and those aren't happening at very short durations all the time, but they're happening over maybe a long period of time. So you can capture that whole load history, and then statistics sort of kick in and allows us to get an acceleration spectral density, which is our input, and then we can also get an output, basically a mean output of our analysis. So I'll show an example of random vibration. This is also something that, if you guys are aware of, a lot of companies will have shaker tables. They'll have shaker tables where they can input these random vibration profiles, and the exact same information that you feed into the shaker table is the same information we feed into the simulation. Whereas on the shaker table, we can actually analyze and look at the part. Did the part break? Did it not? Whereas here we can actually see, okay, this is going to be our stress for a certain percentage of the time, and this will be our displacement for a certain percentage of the time. Also with random vibration is the ability to see sort of where our worst, at the frequency of our worst loading case, okay? So we can plot out a curve that looks similar to what we see on the screen, and we can see what our power spectral density of our acceleration is. That just means, you can kind of see right around 100, it looks like roughly 200 hertz there. We see a peak in this plot, and it's probably a good assumption that at that 200 hertz, that's where we have a natural frequency. So most often these peaks are going to occur at a natural frequency of our structure, and usually it's within some of the first few natural frequencies. Depending on the load direction and things like that, they'll happen usually at the first, second, third natural frequency. And this just gives us the capability to see when that worst case is going to happen at what natural frequency. And then the last type of linear dynamic analysis is a response spectrum. So this gives us a maximum response based on a response spectrum input. So this is most often done with earthquake type studies. The response spectrum is some value that's calculated based on, again, a loading history, and they do some statistics on that, and we get this response spectrum. And a nice example of this is, when people are designing large structures that may be in an area of high earthquake, earthquake frequency, where earthquakes are happening all the time, say in California. And actually the U.S. Geological Survey will actually reports out the response spectrum really anywhere in America. So you can click on a map and it will tell you the response spectrum at that location that you need to design to. And they have a couple of different standards that companies will design to. So response spectrum is again something that a lot of people will do for earthquake type studies. Again, it's a statistical approach to a transient study, but it's giving us a more efficient way rather than trying to capture all the tiny accelerations that are happening very quickly over a longer period of time, say several seconds. Okay, so with that, I'll jump over to SOLIDWORKS here, and I'll show you some quick examples of a couple of these. So the first thing I want to show is the transient analysis. This one is probably the most basic of the linear dynamic analysis because it's sort of easy to understand. With our transient analysis, again, we can enter in, we set up a force, for example, so I've got a 250-pound force at the front of this basketball rim just pulling down on the rim. And if I right-click and edit this, you can see that we can input our force as a function of time. So basically, at 0 seconds, we're going to have this 250-pound force applied, and we're going to keep that force on for a half a second. So we see that our curve here is showing a value of 1, which is basically just a multiplier for what we have entered over here in our box. And then at 0.51 seconds, so right after that half second, we're going to quickly go to 0. We're going to take that load off and then keep it off for 1 second and see what the response is for that last half second. So you can kind of see we have the force on, and then we turn it off and analyze what our result is. Okay, so when we do that, we can look at our stresses, for example, so we can get our response as a function of time. And these ones take a little bit longer to load in because it is reading all the information at every node and over a period of time. So here I'm going to show the maximum stress, at really any given point in time. So there it shows my results. And you can see our yield stress is at 620 megapascals, and we can kind of see we're getting some yielding here where we have the rim meeting the base, and we can, of course, look at the maximum output at any time. So if I edit this plot, we can also plot. So here I'm showing the maximum at any point in time, but I can also plot the stresses at any given time step. So you can see my different time steps here remember, this whole study is running for 1 second, so we can see the different time positions where our load is going to show up. So like if I randomly choose 0.018 seconds, I can plot the stresses at that point in time, so they're a lot lower right here, because again that force, it takes the structure a little bit of time to respond to the load. Another thing we can do then is, so we can show maximum, we can show any given point, but we can also animate this plot. Again, there's quite a bit of data here, and we can see that once we put the force on, it will oscillate up and down, because we have it's going to want to oscillate at its natural frequency. And then you'll see once this gets up to a half a second, you'll see that the force will get pulled off and it'll kind of flip back up. So again, this whole thing is happening at over 1 second of time. Okay, so here you can see those oscillations occurring in our study. It's still waiting, and once we sort of settle out, you see that the oscillations become a lot smaller. So there it is again, pulling down, oscillating a little bit, and then we'll release the force and it will pop back up. So another thing we can do is we can look at a response as a function of time in an XY plot. So here I'm looking at, I'll show this plot here, and we can see that we're looking at the Y displacement at the end of the rim, and you can see that right away we put that 250 pound force on it, and you see that it pulls down and it sort of overshoots, and it starts to oscillate a little bit and settle out to some given displacement at the 250 pounds. And then here at a half second, we let the force off, and it flips back up and kind of vibrates and damps out to really no response. So it goes back to its original shape. As you can see, the value is 0. So again, we pull down, it oscillates and damps out, and then we let it off and it oscillates. So this is a plot just showing the displacement at the end of the rim. And one of the nice things we can also get from this type of thing is we can take a really nice guess at the first natural frequency by just looking at the period of each of these oscillations. So we can see at 0.51 seconds there, it goes up to 0.53. So we've got a period of about 0.02. So we can take that period and solve for our first natural frequency. So if we right-click our results, we can actually look at what our resonant frequencies are, and we can see that the first natural frequency is 38 hertz, and there is our 0.02 second period that's occurring at. So because this first natural frequency is getting excited when we put that load on there, we can actually see sort of how it oscillates and see the frequency that it oscillates at. Okay. So the next example I want to show is going to be a random vibration study. So if you remember this model from last time, we ran a lot of our simulation professional on this. So this is a frame that sits in a piece of construction equipment, and with this, we'd have random vibrations occurring where this thing is going into the working environment. It may be driving over the highway. There's a lot of different load cases for this frame, and we need to characterize all those different load cases. So what we do in the random vibration study is we take all those accelerations that we've measured and we break that down into a base excitation. And when we look at this, you can see that we get a acceleration spectral density from this curve. Now, these acceleration spectral densities can be obtained from acceleration data acceleration data logging software. We can also get these from specifications. There's a really good dynamic specification out there that's free for anyone to look at, and it goes into all these different studies, but it's the military spec. It's public. It's a public document, and it's called military. It's military standard 810, and G is the current version, I believe. But this will give you some basic, cases of acceleration spectral density, or you can obtain your own by instrumenting up, one of your devices or one of your models, and actually run it through a test track. So anyway, we get all this complex data, and then the software will break it down into this acceleration spectral density, which you can see is just a few points on a curve. It doesn't really mean much to the user, but just understand that this is obtained in a well-known way, and you can use this data to simulate and look at a response a lot more efficiently. Look at these random event responses in a way more efficient way. Okay, so we enter in the acceleration spectral density, and then with this, we can look at stresses. We can look at our root mean square stresses. What that means is the values that I plot here for stress, it's the root mean square value, and it's a 1 sigma value. So 1 sigma value means that the stresses that we're looking at right now on this model will happen 68.2% of the life of the loading history. Okay, so the stress values we're looking at will 68.2% of the time will be at this value or less. Okay, and then if we multiply these values by 2, everywhere in our model we get a 2 sigma value, which means that 95.5% of the time that results will be at or less than 2 times the value that I'm showing here. And then if we do a 3 sigma value, which is often where people stop, a 3 sigma value, we simply multiply all these results, multiply all the values by 3, and we can say that the response is going to be at this value or less 99.7% of the time. So it's looking at the statistical input that we have with our acceleration spectral density, and then giving us a statistical output. So just looking at the different standard deviations. So 1 sigma is 1 standard deviation, 2 sigmas, 2 standard deviations, and 3 sigmas, 3 standard deviations, which is 99.7% of the time. So with this, we can look at things like stresses or displacements. For example, again, this shows us that root mean square value, just telling us that this will be at 0.175 inches, 68.2% of the time. And then if we take this 0.175, multiply it by 2, so we get a value of 350 or 0.35 inches. We can say that 95.5% of our loading case will be at 3.5 inches or less, and then if we multiply 0.175 by 3, then we get that 3 sigma value. So we can plot these RMS values, giving us sort of the statistical result. And then lastly, we can also look at these PSD curves, so power spectral density of as a function of frequency. So what this tells us is we can look at this and actually see where the highest response is occurring, similar to the harmonic analysis, where we can see where our frequency is, what frequency, operating frequency would be the worst for us. And here we can look and see that our peak is occurring at about 14 hertz, a little over 14 hertz. And if again we look at what our first natural frequency is for this, I can list my resonant frequencies, and we can see that our first natural frequency is at 14.1, and that makes sense because we see the worst response at that frequency. So that's a quick rundown of some of linear dynamics capabilities. So next, I want to jump into nonlinear studies. So if we look at the nonlinear studies, I'm going to first cover a nonlinear static type study. So nonlinear static studies give us a couple of capabilities that are again common in engineering problems. This first one shows real nicely how the stiffness of the structure will change throughout its loading case. So with this clip, when we're sliding the clip on, it hits kind of the front edge hits, or it hits the front end of the circle, and then sort of needs to work its way around. Well, when it's working its way around, it gets to a point where the force that you're applying actually, once it gets around kind of the widest opening and it starts sliding around the backside, now all of a sudden we don't need to push it as hard for it to snap into position. So the stiffness of our structure is changing throughout the loading history, and that's something we cannot do in linear statics. In linear statics, we assume that our load case is, or we assume that our stiffness isn't changing, and it's calculated as the first thing the solver does, and it doesn't get recalculated ever again. So here you can see that the stiffness is changing, and it's also recalculating the contact stresses as this little clip moves around the circle. You can see that we get different stresses at the contact location. Another example of nonlinear behavior is things like a threaded bolt. In this case, you can see as you're putting a tensile load on this, that the teeth, you can see if you focus in right here where the teeth are, you can see that the stress distribution is changing, meaning the contact area of the threads is changing. So really, if you want to analyze a sort of the teeth within a bolt, nonlinear is really the only way we can cover this because of how the stiffness is changing throughout the loading history. And then another good example for nonlinear is nonlinear buckling. So nonlinear buckling allows us to look at a sort of the post-buckling shape of something. So here we're applying a force at the top of this plastic bottle, and you can kind of see where we see that red, that this is a displacement plot, and you can see that it wants to buckle inward, so that this is a case of buckling. So buckling is just an example where when you're pushing on something and the stiffness, the stress stiffness is softening the structure, all of a sudden there will be a point where as you're loading this, all of a sudden it becomes very, very easy to compress this, and that's where buckling occurs. And with a nonlinear buckling case, we can capture this and look at the post-buckled shape, so we can actually see what the bottle would look like under some load. So those are a couple of nonlinear examples. So nonlinear also allows us to look at plastic and rubber materials. So another huge thing we get with the nonlinear solver is the ability to apply different nonlinear material properties. So we need nonlinear material properties whenever we go beyond the yield strength of a material. So with linear statics, our material curve is linear. Our stress strain curve is linear up until the yield point. Once we get beyond the yield point, the stiffness of the material actually changes, and it takes less energy to deform something. So the nonlinear solver allows us to enter in a stress strain curve or a nonlinear material model for both things like metals, plastics, and rubbers, where we're looking at the post-yielding behavior. Now with rubbers, we have a hyperelastic material model, which allows us to capture the things like rubbers that will actually, stretch to a very long, or that can take a lot of strain because they're stretching a lot, but really not have a very high value of stress. Those types of materials actually have a different shape, material stress strain curve. So our hyperelastic material model is best used for those. And then it also mentions this type of analysis, once we go beyond yield, if we load something and then take the loading off of it, it will actually show that post-deformed shape, so it won't return to its initial shape, so it will have some permanent deformation. So that's what we can solve. So I have an example of that coming up. They mentioned we can simulate large deflection effects. So large deflection is a case where the stiffness of our structure, again, is changing where we can't account for that in a linear static solver, but with a nonlinear solver, we recalculate the stiffness. So as something loads, the stiffness of the structure will change, and if we're deforming a lot, our stiffness needs to be recalculated to be accurate. I mentioned the contact analysis with the clip example, so anything where we're pushing or sliding against the surface and the stiffness is changing at that contact area, that's going to be something that needs to be run with a nonlinear solver as well. And then I mentioned, the material strength variation with temperature change. We can actually account for that, as well as doing nonlinear buckling, where the shape of our material is buckling, or the response of the material is quickly deforming under kind of a pretty constant load, or just slowly increasing that load. So we have this instability in our geometry. So I will jump back to SOLIDWORKS and show a couple more examples of this. So the first thing I want to show is this paperclip example. So here we're applying a small force. We're just going to grab this end here, and we're going to push it up with 1 Newton of force. And the load case here, if I edit that definition, I'm also applying this with a curve. So what's going to happen is we're going to run this, and we're going to push it up. So at 0.1 in time, at 1 second of time, it's taking on the full 1 Newton force, and then at 2 seconds we're going to let it go back to 0. So we're going to push the force on there, and then we're going to let it go back to 0 at the end, and we'll see what we get for our post yielding case. And this one, of course, has the nonlinear material property, where we can enter the stress strain curve, or we can simply put in this tangent modulus, which is basically just the stiffness beyond yield. It's similar to our elastic modulus, but it begins at the yield stress value. So if we look at the stress at 1 second in time, this is under the full load case, you can see that we're just going beyond yield at a few locations here, and getting very close to yield down here at this end. And then if we show the stress at 2 seconds, we can see that once we take the load fully off, we see that it has this permanent deformation. So our paperclip won't go back to its original shape unless we apply some force and kind of bend it back to its original shape. So with the nonlinear solver, again, we can set up these different loading histories similar to the transient study, where we're entering in a load curve where we have a force going up, and then we take the force off. We could put the force on and then actually bend it down as well, and you can see that it will retain some of this stress after deformation, or after our load is no longer applied, as we can see in this plot. Another example I have is that latch that we saw in the video, but this latch is done with a 2D simplification. So if we look at the latch, we can see that what we're mostly concerned about is kind of this section here, and of course this circular section, and some of these sides that will prevent movement outside of that. So we use a 2D simplification in this case to speed up the analysis. So dynamic and nonlinear analysis take additional time to solve because they're more complex, but this allows us, using 2D simplification, allows us to run these studies a lot quicker. So here I can show the stress in my 2D section here, and if I just take a top view, we can kind of see the stress at the ending time. But if I animate this plot, you can see that our stress along that, if I slow that down, we can see that the stress along the clip here, it needs to change that contact stress so that the contacts are, the location that's in contact with the circle is actually changing as we move around there. And here, of course, we can see the stress as a function of this time, our nonlinear time here, so we can see what the stresses are and see our maximum stresses occurring down here on the clip. Now the nice thing about 2D simplification is I'm showing the plot in 3D, when in reality this is meshed as just sort of a flat surface everywhere, and then the result is extruded. So this is really all we're doing the simulation on, is a flat surface that we can get with we can really refine our mesh. If I show it here, you can see how refined that mesh is. Okay, and this thing really doesn't take very long to solve, because again it only needs to do this simplified 2D case that we can extrude into a more complex looking result. Okay, and then another example I want to show is just a kind of a rubber gasket example. Again, we'll use 2D simplification, but this time we'll do an axisymmetric. And with this, we're simply moving our we're pushing down this top to get some gasket compression here. So if I look at the stress plot, you can see that we're looking at the result in the 2D simplification form. And if I animate this, we can see how the contact stresses again are changing. So as this rubber gasket gets compressed, it becomes a lot wider and actually has to distribute the stresses along a flatter face rather than that round face that we initially have. Another thing that we see here is we have this large deformation, this large localized deformation at the gasket. So again, the stiffness of this circular shape it's a lot stiffer at first, but as this starts to compress, the shape becomes less and less stiff. So as we push this down, the force required to push this down actually decreases, because our stiffness is lowering as well, or decreasing as well. And similar to our previous 2D simplification, we can also show this, really as any angle that we want. So here I'm showing the result as a 3D plot, showing 330 degrees, and of course we can animate this as well. So as we push this down, actually the highest stresses are occurring right here in the corner. So 2D simplification, whenever it's applicable to your nonlinear studies, it becomes very, very efficient to run problems in this way. So a lot of people will run 2D simplification on their nonlinear just to make them more efficient. Okay, so the next thing I want to talk about, I'll jump back to my slides here. The next thing I want to talk about is nonlinear dynamic studies. Okay, so nonlinear dynamic studies are going to be our highest or most complex types of studies. So a good example is kind of shown here in this video is a collision between two objects, and you can kind of see how this chair or this frame is sort of vibrating after the heavy ball hits and kind of bounces off of it. You can see what the reaction looks like. So in this case, we have a very complex thing occurring because we're putting the load on. The chair is vibrating because it's responding dynamically, and we're also doing this time history. And so and you can kind of see in the flat surface where that contact changes as this ball drops further and further. We see that high peak stress sort of occur in the flat section, and then it goes away, and the frame oscillates and gets damped out. So if I jump over to SOLIDWORKS, I do have another example of this with a softball bat. So the softball bat shows us sort of what happens when a bat connects with a ball. So another nice thing I did here is I sort of cut this in half because I can use symmetry to solve this type of analysis and again speed it up. So I've cut this in half, and if we look at what I've got here is that I'm taking the bat and moving it at about 80 miles per hour. You know, it's kind of an average swing speed, and I'm just sliding it kind of along a plane. That's what all these all of these restraints are doing. They're keeping it on this plane. I have the initial condition on the bat moving at 80 miles per hour, and then the ball is sort of sitting still. So then when I look at the stress here, and it's nice because I can sort of zoom in here at this contact, we can see what that contact stress is on the bat as well as the ball. So here I'm showing this at the first, you know, at the initial collision. So my time step here, notice, is very, very tiny because this is a high frequency event. But of course we can animate this and actually see what's happening. We can see the stresses, you know, once they separate, get to be very small, but we can see the high stresses on the bat at contact. Another thing we can look at is, you know, resultant displacement. Now, with this, you'll see that the ball will increase because it starts to move away from its initial position. But one thing I like to show on this bat, if I sort of zoom in, notice the bat, once it contacts the ball, it's actually oscillating as well. So it's kind of vibrating back and forth as after that contact occurs. It's rocking back and forth. And again, it will vibrate at its first natural frequency, most likely, maybe the second natural frequency. And then when we have a nonlinear dynamic, we can also plot velocity, because the nonlinear dynamic solver is actually solving the full equation, of motion for damped force vibration. So it's solving this full equation, so we can actually plot things like velocity in this as well. So if we look at the velocity plot, you can see that initially the bat will have all the velocity, but then the ball is actually coming off at a much higher speed. Now this one's at a higher deformation scale, so it's a little bit easier to see that vibration. So I've upped the deformation scale to 5 times, so we can see the bat move, sort of oscillate back and forth, and you can see the velocity is a lot lower, kind of at the tip, because it's bending back. And then if we look at the other side, again, this is at a higher deformation scale, so we'll see overlapping, the faces overlapping at first because they're showing a higher deformation than what would happen. But we can actually see that trampoline effect occurring between the bat and the ball. So the ball is actually coming off at a higher speed than the swing speed would be. So very common in bat design is to sort of try to maximize this trampoline effect, and there are a lot of companies that do this type of analysis to get the best bat performance. And then similar to the transient study I showed earlier, we can look at the response as a function of time. So here I'm showing the velocity of the ball as a function of time, and you can kind of see that during the contact it starts to pick up, and you can kind of see here's where an oscillation of the bat sort of is occurring, and also that trampoline effect. So we see this odd behavior, and then once the bat comes away from the ball, we can see that it moves off at some speed, and this speed is actually higher than the bat speed, our initial bat speed that we had set up as our initial condition. So the next thing I want to discuss quickly is composite layups. So the last thing here in the slides is our composite layup capability. So composite layups are going to be carbon fiber oftentimes carbon fiber layups where we have these different layers of carbon fiber laminate, and these layers are situated in a way to orient the fibers, the carbon fibers, in specific directions. So so here you can kind of see this carbon fiber layup has its fiber orientation shown, but we can actually take the different layers and say and apply a thickness to each layer, and then also what direction are the fiber orientations. So we can also get some additional capability on our post-processing where we can actually predict individual layer failure, so maybe where there'll be cracks or where the layers will delaminate from each other. We can look at the laminate strength for different fiber orientations. Also look at the inner laminar shear stresses. So again, looking at things at the layer level gives us a nice post-processing feature for these types of materials. So again, a lot of storage tanks, a lot of high-pressure storage tanks are made this way nowadays. Building panels, marine and furniture and automotive, aerospace industry. So there's a lot of this type of carbon fiber layup in these types of in these industries. And actually, in the softball bat, those bats are also made with carbon fiber layups. They're top of the line bats are made with carbon fiber layups as well. So if I jump back over to SolidWorks and show this last example, we can see that we have just kind of this mountain board that we're sort of we're applying a force to simulate jumping off a jump and then landing. So we have a couple of forces here, and then for the carbon fiber layup, if I just edit the definition of our material, here you can see that this is done in such a way that we have our different thicknesses. So we have a 0.25 millimeter thickness, and this first layer is at a 0 degree orientation, so you can see the orientation there. And then if I click on the second layer, it's at 45 degrees. Third layer is at negative 45 degrees. And then the fourth layer is at the same angle. The fifth layer flips back. And then the sixth layer is straight again at 0 degrees. And then we have a completely different material, balsa wood, in the middle. And then we continue on with, and then we have the opposite on the other side. On layers 8 through 13, we again have the same pattern of 0, 45, negative 45, negative 45, 45, 0. So when we do that, not only are we're applying these more complex material properties because we have this directionality associated with it, we can also look at stresses for each layer. So here you can see my stresses for ply number 1, so this would be on the bottom layer. And then if I simply edit that definition, I can move it up to the next layer. We can look at 2, and you can see how the stresses change for the different layers. We can also look at things like factor of safety at each layer. So the minimum factor of safety in this case is 4.6 for this bottom layer. So oftentimes on a board like this, your worst cases are going to happen usually on the top or the bottom layer, so the first or last layer. So we can look at the factor of safety on these different layers, or we can look at the worst case factor of safety anywhere in the model. So these in this worst case, it's actually taking the layer, that individual layer, whatever its worst case is, and plotting that all in a single plot. So these worst cases can be happening at different layers, but this gives us a general overview of where that worst case, or what the worst case factor of safety would be anywhere in the model. So you can see it drops down to 3 because the worst case may be happening at different layers, different locations in different layers. A couple of other plots we can do are looking at interlaminar shear. So we can look at the interlaminar shear of the different, between the different layers. So we can choose that, and then also this occurs at for each layer, and we can actually get a plot for that interlaminar shear stress as well. So that kind of concludes the presentation and the webinar. If there's any questions, we've got some time here to answer a few questions. Otherwise, I'll kind of leave up our contact information, so if anything comes up down the road, if you have any additional questions, you can contact us.